Assalamu alaikum. I welcome all of you to organic synthesis class. Today we will be discussing reactive intermediates, and many students, many organic chemistry students, they know what reactive intermediates are. They are familiar with them. So intermediate, what actually is an intermediate? Intermediate is a species which is produced in a chemical reaction, and in that same chemical reaction it is consumed in most of the cases. So there are some very familiar looking intermediates which majority of the organic chemistry students know. They are just like carbocation. This is carbocation, free radical, carbonine. These are the ones which students are familiar with, but there are other intermediates too, and they are a little bit different, and maybe some of the students may have not heard their names. They are odd looking things like carbon with the two bonds. This is called carbine, and another one is a species like this. This is called nitrine, and this one, it is called benzene. When it is in different aromatic groups, it's also known as arine. So today we will be studying one of them, the carbines. That what actually are carbines, and what are their structures, and how they react during a chemical reactions, and what are their and how they are produced. Carbines. They are a species which has the carbon. In carbines, the carbon has just two covalent bonds and has non-bonding electrons, two non-bonding electrons present on it. I didn't mention or intentionally that these are lone pair. They are not a lone pair, so I said that there are two electrons present on a carbon. Okay, so these are carbines. Divalent species means they have two bonds, covalent bonds. They could be or can be another carbon, hydrogen, oxygen, etc., etc. These can be hydrogen. It could be carbon. It could be oxygen, and it could be some other elements or atom. And same is the case of this thing. The carbines, they have total of 6 electrons in it. 6 electrons, just like 1, 2, 3, 4, 5, 6, 2 each in a covalent bond and 2 on a carbon atom. So it is a divalent and 6 electron species. So what this means, it's just like a carbocation. For example, let's compare this thing with the carbocation. The carbocation, it has again 2, 4, 6 electrons, but all the electrons are present a part of a covalent bond. So it is a 6 electron species. This is a 6 electron species, but this thing has an electron pair on it, and this doesn't have any. This thing has 2 electrons present on the carbon, and this species or this intermediate doesn't have any electrons present on the carbon, but this one has a net positive charge, and the above one has carbines are electrically neutral. So if you want to calculate its formal charge, so there are simple formulas for the formal charge calculation, and when you apply it, you will find out that this thing is electrically neutral. Structures of the carbines. So the carbine exists in two geometries. One is called as the bent one, and the other is called as linear one. So let's move to them. I am writing the geometries of these methylene. This is one. The other one is like this one. Both are almost similar, but their electron fillings are a bit different. The third one is like this. Now, what actually they are, so this is a bent structure, bent in a sense that when I fill the electron in it, you will know that how it is bent with respect to what it is bent. So in this structure, it is, suppose this one is singlet, so two electrons are present in one orbital. This one is called triplet, one electron in each orbital is present. This one is again called as a triplet, and one electron in each orbital is present. This is singlet, this is triplet, and this thing is again a triplet one. Now let's coming to the orbitals, what these orbitals are actually. As you see that this one is a p orbital, and this is some hybridized orbital. So the hybridization of this one, this carbene is sp squared, or sp2 you call it, sp squared. This one again is an sp squared, and this one is sp, hybridized orbital. But their arrangements of electrons are different. So what about this one? As you know that from the hybridization point of view, that when sp squared hybridized orbital, it is lower in energy than the p orbital. When hybridization occurs, as you know, the energy of the orbital decreases because s and p are mixed in different ratios. So here, as you see that it is sp squared orbital. So this one is the carbon forms 3 bonds with the sp squared orbital, 2 bonds, and keeps lone pair in another sp squared orbital. This is sp squared, this is sp squared, and this is sp squared. Okay? So the carbon forms 2 bonds with an sp squared orbitals and keeps 2 electrons in an sp squared orbitals and keep the p orbital vacant. So this is one geometry or one structure, that how carbon's electrons are present inside the carbene. The other structure is this one here. As you see that one electron each is present in both orbital. One electron is present in an sp squared one electron, and the other is present in a p orbital. It is a 2p orbital, of course. sp squared, sp squared. Now coming to the third one, it is sp hybridized. So this one is sp. Sigma bond is formed between the carbon and the hydrogen with an sp orbital, again an sp orbital, and as you know that these are p orbitals where the electrons are present. So these things are odd living species. It seems very much difficult for first time when students see it, and too difficult to understand it how they are and how they look like. So I would try to give a sort of analogy of this structure to some other things, and I think that you will understand from that one. Now let's go. As you know that carbon can form two bonds. It's a carbon-carbon double bond, ethylene. It's ethene or ethylene or whatever it is. So it's ethene. As you see that this carbon is sp squared, so it is forming one bond with, let me change the color of the pen, I think it may create a problem. It is sp squared. So the carbon uses two sp squared orbitals to form a covalent bond, and other sp squared orbital form bond with the carbon. So the carbon is using three sp squared orbitals as a sigma bonds. Okay, one with the carbon, the other with the hydrogen, the other with the hydrogen. And these are hydrogen, these are not nitrogen. Okay, so okay, don't be confused. So let's suppose that I delete this thing, and you will know that what p orbital actually is. The p orbital, would that I had multiples of markers. This is a p orbital and this is a p orbital. Okay. So the pi bond is produced by the lateral overlap of the p orbitals. Okay. Now suppose somehow I delete this half structure. This is not a true representation of the carbene, but I just want that how those orbitals are present, and you should understand, and it will help you to understand what this structure look like. Okay, I am just doing it for you people to understand the above structure. Let I delete those things, delete or erase. Okay, now what happens? This blue one, 2 electron, this was again a sigma bond, but now no carbon is present, so 2 electrons are present in the sigma bond. Suppose I just place 2 electrons here and the rest of the molecule is deleted. So it is like the molecule look like this. It has a p orbital and a sigma bond. Now as you see that these are this CH bond is sp squared, this CH bond is sp squared, and the lone pair is present in an sp squared orbital. Okay. What about this thing? It is again the same thing. It looks like the same thing, and it is in fact the same thing, but the electronic arrangement is different. This has one electron and this p has another electron. Here the p is vacant. Here the p is filled. Now, as you know that the sp squared orbitals or the hybridized orbitals, in most cases, they are lower in energy than the p orbitals. Okay, unhybridized p orbital. So as you see here, one electron is present in a high energy orbital, and the other is present in a lower energy orbital. And here, both are present in a lower energy orbital. So look at this thing. So if how the electrons are present, this and this is the p. This is the sp squared. So here both the electrons are present in the sp squared orbital. And what about this one? It is again p. It's a 2p orbital. Okay. So and this is sp squared. So here one electron is present here and the other electron is present here. So it is another representation that you can see. This one is called as a singlet carbene, S for singlet, and this one is called as a triplet carbene. But which one is stable? What thing will be deciding that which one will be stable? So when we look to the structure, it seems that this thing is stable because both the electrons are present in a very lower energy state, and this thing is not stable. So all the molecules when come to the ground state, its ground state should be the one which is stable, lower in energy. But here we are forgetting one thing or missing one thing, that 2 electrons are present in an sp squared orbital, okay, and this sp squared orbital is very small and repulsion might occur. There may be some repulsion. So this repulsion, due to this repulsion, electrons prefer to be present in a separate orbital. In reality, when these are hydrogens or carbons, etc., the lower spin state, the lower state of the carbene is the triplet one. Because due to the Coulombic interactions or the repulsion between the electrons, this state, though the electrons are present in lower energy orbital, but the energy exceeded, it repel each other and increases the energy so much that the triplet is the triplet state is lower in energy than this one. Okay. Now coming to the third one, this is another option, and these are very rare. These are extremely rare. Okay. Look at this. This is sp. So how to understand this? May I give you another analogy, but for just to make you understand. This is, suppose, a triplet. Alkyne. How alkyne is formed? As you know that in alkyne there are sigma bonds. I would write these sigma bonds with lines, okay? And there are again p orbitals present, okay? This p orbital is like this, and both of them literally overlap with each other, okay? The other thing, there is another orbital present in it again, and both these orbitals are perpendicular to each other. What I mean from perpendicular, this green one is like this, and the green one is like this, and the black one is like this, okay? So this is the p orbital, and the same is the case here. If there is one p orbital overlapping with this one, there should be another perpendicular to it overlapping with the orbital, okay? So they are overlapping with each other. Now suppose somehow we replace this carbon with hydrogen and erase everything. What will be left behind? Hydrogen. Okay, so this species is like this one. So this is called straight or linear species, in which the electrons are present in 2p orbitals. Here this thing is again very much lower in energy, because it is lower in energy because the sp hybridized orbitals are actually very much lower in energy. But 2 vacant p orbitals, now 2 electrons are present in the p orbital, so it makes its energy very high. So I hope you people might have understand this. So let's come to the angles between these hydrogens or the ligands or the substituents. Okay, this one and this one. 100 to 110, and this angle is 130 to 150, and this one, of course, the angles between these two substituents or hydrogens, okay, and this one is 180. It's like this, and it's triplet state. Now this is a singlet, this is a triplet, okay? So why I have a question for you, that why this angle is smaller and this angle is a little bit bigger? Because even there are 2 orbitals, and here there is 1 orbital. There is a solid reason for it, because here when you look at this thing, both the hydrogens and the now you can call it a sort of lone pair. This lone pair, they are present on a same plane, in a same plane. I mean, these are the hydrogens, and it is present like this one. Okay. Or may I have a small balloon, which might be very useful. Look at this. So it can, look at this, just because of this thing, it repels them or make them near. So its angle is smaller. Okay? Now coming to the angles between these hydrogen, as I mentioned that the angle between these two hydrogen is 100 to 110 degree, and between these two hydrogens, or it might be another substituent, it is 130 to 150. So this one is like this, and the other one is like this. It's bigger. Why? So I explained this with the help of a balloon. I think you understand that lone pair repel the bond pair very much, but the lone pair should be present on the same plane, in the same plane, in order to be effective. Now what about this one? It has 2 electrons, 2 orbitals. Now 2 orbitals may have, or it should push the hydrogen even further if one sees, but it's not the case. Look at those hydrogens. Both the hydrogen, this one is on the back side of the board, this one is in the front side of the board, so they are like this. Okay. But these two things, orbitals, one is like this one, and the other is above like this. Okay. So both these orbitals are perpendicular to the bond angle, so they are not as effective as this one is. It is pushing them very hard, and the other can't push them very hard. Just like this one. Suppose this thing, it can push them directly. Look at this. Suppose this is a lone pair, it can squeeze them very much. Okay. But what about something if they are not on the same plane? This is like this. Okay. And one is like this, and the other is like this. So they are not pushing them. Okay. Very hardly. Now coming to another thing, very important thing. What about the carbines with ground state which have ground state singlet? There are some carbines which have singlet ground state, but there is a condition for them, because so far as we discussed, or we know that carbines, majority of the carbines, they have their ground state, or the lower energy state is a triplet one. Okay. So this thing wins. Majority should have a triplet ground state, and I am not mentioning this one, and I will come to this thing a little bit later. Now, so what about carbines? Suppose there is a carbine like this. These might be some substituent, hydrogen, or etc. etc. But what if you replace one of the hydrogen with oxygen? Or nitrogen, oxygen, nitrogen, or some halogen. Now suddenly the singlet state become very important or lower in energy. You know why? Because as you know that the nitrogen, oxygen, or halogens, those have lone pairs on them. Okay, and those lone pairs, so these are the lone pair, it could be donated to this orbital. So these lone pair stabilize themselves or make a bond with a pi bond with this thing. Now these orbitals, the energy of these orbitals is a bit higher, or you can say that these are now filled. These electrons are bound or forced to live in sp squared orbital. So these are ground state singlets. Okay, and let's look at this with some another angle. This is the lone pair and this is the carbon orbital. Okay, so it can be donated like this. It can donate it to this one, so it's become a pi bond. But a pi bond is not like this. When it start donation, this lone pair or the hybridization of this nitrogen again changes to what? Sp squared. Here it is sp cubed hybridized, but now it is sp squared because suddenly a pi orbital appeared here. Okay, so these, now when you see a carbene with oxygen, nitrogen or halogens, just like fluorine, chlorine or bromine, most of them, so those will be ground state singlets. Okay, now what is the evidence? Because science needs evidence that how the science, how we can say that these are singlets or these are triplets. There must be some evidence for it. This evidence for the singlet or the triplet is comes from ESR. What actually is ESR? Electron spin resonance spectroscopy. But it's not relevant to this course, and majority of the students might not have studied that, but it's very much similar or like nuclear magnetic resonance spectroscopy. And what does it tells? If there is one orbital, okay, if there is a single electron present in an orbital, so what will happen? It can detect it. Okay, coming to the structures, that what is the evidence or the proof that these structures are triplet or those are singlets? So because those carbines, they are very much reactive, and it's very difficult to determine that with normal instrumentation that how they are they singlet or a triplet. The most important thing or the most easiest way is to know that which one is triplet, which one is singlet. As you know that the unpaired electron species, they are paramagnetic. So this is one evidence. The other evidence comes from another technique which is called as electron spin resonance spectroscopy. It's very much similar to that of the nuclear magnetic resonance spectroscopy, where there we study proton and here we study the electron. So those unpaired electron species can be determined by ESR or electron spin resonance spectroscopy. It can tell us very much easily about that. X-ray can also tell us, but as you know that these are very reactive species, and for X-ray you have to make a crystal. For a crystal you should bring all the molecules together, but when you bring those things together, they are extremely reactive, and they will react together and form other molecules. Okay, so X-ray is not very much effective right here. And how can we say that those carbines, they are electrophilic in nature? So there is another technique called nuclear magnetic resonance spectroscopy, which you will study in spectroscopy course, that can determine it. Okay, suppose these are nitrogens, and very huge groups are attached to these, very huge, and here is a carbene. Okay, so the values, these are carbines. So what NMR gives? C13 NMR gives some values, and it gives a values of 211 part per million. So what this value mean? Because it's not important for you people, but just this, what this number mean. The bigger the number, the more the electrophilic the carbon is. So NMR says, or NMR value gives that this has a very huge number. This is 2 111. So this thing is very much de-shielded, you can say, or it is very much electron deficient, or it is electrophilic. And why they selected this species? Because these groups are huge. They are so huge that just because of their size, this carbene is very much stable. It stabilizes it. How it stabilizes it? Because two carbene cannot come near together and react. They can't reach each other, and they can't react just because of these two big groups. So this was the species which for which NMR was carried out, and NMR values proved that the carbines are carbenes are electrophilic. Okay.